Guys, we are moving on to a new chapter. Elastic stability of columns. Elastic stability of columns. Or people simply call it as buckling of columns. Buckling of columns. Now we have already learned what is a beam. Beam is a structural member which takes transverse loads. So that means longitudinal means along the length, transverse means perpendicular to the length. So beams are those structural members which take transverse loads, and columns are those which take the load. Suppose if it is a column, then we are applying a load like this. These are columns. The pillars of the building are columns, and the one which actually supports the floor or the roof of the buildings are called as the beams. Okay, so these are called as columns. So columns take the load along their length. Now we know that we already learned from the very first chapter that stress is equal to P by A. Stress is equal to P by A. Stress is equal to P by A. So if this load exceeds, which makes the stress to go beyond the allowable stress, then I say it is going to fail. So we have seen the stress strain diagram. We have seen the stress strain diagram like this, something like this. So this is the yield stress where the material plastically deforms. So that means it loses elasticity at this point. Up to this point it is elastic, and beyond this point it is plastic. Okay, we know that. So this allowable stress, yield stress are the same. Okay, so the material, now the stress in the material should not go beyond this yield stress. If it goes beyond the yield stress, that means the metal would have changed shape. If any component whose shape has changed, will you buy it? An handle lever, this brake lever or the footrest or any handlebar, if it has changed shape, so that means it has already taken load beyond its capacity and it has failed. Okay, so you need to replace it. So usually you don't go beyond it. Now I have a simple demonstration for you. I got this stick from the same material here. If you are trying to compress a small stick like this, it becomes very difficult for me to compress. It's not that easy. I'm not able to even break it. Okay, I'm actually trying to compress a small stick here like this. But the same material stick, if I hold it like this, if I actually try to apply load, it's going to break. So that means there is something beyond just the equation sigma is equal to P by A. So we have not included the length factor. Suppose if any structure is short, that means it can take more load. Okay, because they will not actually change shape. But if they are long, then due to some eccentricity in the geometry of the beam, it starts bending to one side and it starts failing like this. And if I apply more load, it breaks into two pieces. So I think people felt there is something has to be done for this equation, because it is not right. It is only suitable for short lengths. It is not suitable for long lengths. You can't apply this equation sigma is equal to P by A for a very long column like this, because they will not take so much of load, because this is only for compressive loading. Where you can use this. So suppose if a shaft is very short like this, then you can use this. Suppose if not a shaft, a column. Suppose if it is very long like this, then you can't use this equation, because when it is short, these usually fail because of buckling. Fail because of the compressive loads. They start to swell like this onto the sides and they fail. At that time you can use this formula. But if it is very long, then this actually starts to bend like this. they start to bend like this and fail. So this phenomena is called as elastic deformation of the beam, okay, in the lateral directions, which is also called as the buckling of columns. And some people also use this word crippling of columns. Buckling and crippling, both they use. So crippling of columns or buckling of columns. Now almost around 300 years back, a famous mathematician who actually did a lot of work even in the other fields also, he actually came up with few equations where people could use for solving the load that could be taken by long columns. For short columns, you can use this formula. For long columns, he actually gave an equation. And okay, I'm really surprised, okay, around 300 years back. So now what is the name of the person I said? Euler. Euler gave an equation. So Euler gave an equation. So the equation that he gave is called as, it is still famous and it is still being used, and that's called as the Euler's equation. I write it as P. What is P basically? Load. Is it visible in the camera? So P stands for load, and if I say PCR, so can you guess what is this PCR? So crippling or buckling. Okay. So buckling or the crippling load, and people may confuse it with the crushing loads. So crushing loads means this is the crushing load. That means it actually crushes a short piece. When it's a long piece, it starts crippling. Okay. So both crippling and this crippling and crushing have both CR in the front. The two terms. Okay. So PCR, he gave. What I'm writing is the formula given by whom? Euler. So Euler's formula. This is called the Euler's formula. This is still being used. What he gave was pi square E I minimum divided by LE square is the formula that he gave around 300 years back. So in 2024 we are studying this, and we should be able to just understand what he has given and solve a few numericals on the formula on what he has given. Now in this, everybody knows pi, it's a constant. Do you know E? E stands for Young's modulus. E stands for Young's modulus. It will be like 200 GPa or something for steel. For copper it will be 100 GPa. Now everybody knows I, no? Everybody knows I. What is I? Moment of inertia. For rectangular sections it is BDQ by 12. So moment of inertia. Moment of inertia. Now here it is given I minimum. What does it mean? So anybody has got a scale? Now, okay, here's the guys. Basically, if you consider this scale as a column, if I try to apply loads on this scale, don't worry, if it breaks, I will give it. Okay. Now, if I try to apply a load, now the scale starts crippling like this. Now there are two ways. Can the scale bend like this? Can this scale bend like this? No. But the scale can bend like this. So when you actually have a section, when you've got a square section like this, suppose if there's a square section, so that means I about xx, if you call this as x and if you call this as y, then since b and d are same, bdq by 12 will be same for xx section and also yy. Suppose if it is a rectangular section, then if you take about xx axis, that means then this b will be smaller, d will be larger, right? So ixx will be larger, but iyy, if I take iyy, then this will become B. So Iyy means basically I am trying to imagine like this. This is Y. So this becomes B, this becomes D. So then this value of BDQ by 12, BDQ by 12 in this case will be smaller because D is smaller. So imagine that this side is 1, this side is 3. So you got a rectangle of one shorter side 1 and this side 3. What will be BDQ by 12 in Ixx? What will be BDQ by 12 in Ixx? 1 into 3 cube divided by 12. So how much is it? It is 9 by 12. 9 by 12. Now if I want it about y axis, then this becomes 3. This becomes 1. So then Iyy will be how much? 3 by 3. So 3 into 1 cube divided by 12, which is 3 by 12. Which is larger? Ixx is larger, Iyy is smaller. So Iyy is smaller compared to Ixx, which means that it is going to bend about Iyy. So that means it is going to bend about Iyy. Understand? Now this column is going to get buckle about a section where it has got least resistance to bending. Okay, so he wants us to substitute the lower value, because when you are applying load, the column will try to bend towards the least resistance. Okay, so that is I minimum, and LE is the effective length. Effective length. Suppose if it is the length of the column, then you can't take this length as the same length, because this LE depends on what is called as the end conditions. End conditions. So now, as an introduction to this chapter, so we will now learn what are the 4 end conditions Euler mentioned. Okay. So the 4 end conditions are, I will show you now. Guys, in this equation, most of the things you know, and what you don't know is about LE. So I'll write these end conditions now. So okay, I'm writing for LE, effective length. So LE stands for effective length. Effective length depends on the end conditions of the end conditions means how you hold it. Guys, how you hold it really matters. Guys, how you hold it really matters. Suppose if I actually hold it like this, if I hold it like this, can you take more load? Definitely. If I hold like this, will it take more load? No. So the way I hold really matters. How much load these columns can take. So therefore Euler said you need to substitute different LE values for different end conditions. So the first end condition is something like this. So that means here is a inch, and here you are applying load. And as you apply the load, both ends are allowed to bend. Both ends are allowed to bend like this. So you apply a load, both ends are allowed to bend like this. In this case, he says effective length has to be taken as the same length. If the length of the column is 1 meter, then the effective length has to be taken as 1 meter. The other case is one end fixed, other end free. So that means one beam is, this column is going like this. Here you apply load. As you apply load, what happens? Because of the application of the load, it starts going like this. Understood? So now this column starts going like this. and basically the effective length of the column, if you extend to the other side, it looks like a column. Okay, I'm trying to see the arch here. So the effective length LE is 2 times the original length of the column. So if this is L, the effective length of the column is like 2 times the length. So that means if this column is 1 meter, if you hold like this, how? One end fixed, other end free. Guys, let me write here. Now what I should write here? Both ends hinged. Hinged and free are different. Hinged means like door hinges. It's like door hinges. Free means simply apply load and it can move any side. It can move any side, but it is restricted here. It is restricted, it is allowed to bend, but it here, as you apply, it is not restricted to move only along this path. It is free. This end is free, this end is fixed like a cantilever. You know how a cantilever is fixed, no? Like this. In the same way, it is like a vertical cantilever like this. It is a vertical cantilever like this. So when you have that, then LE is equal to how much? How much? 2 times the original actual length. So now what do you call this as? Case B as what do you call this as? So this, so I'll write it here. So much time left? 5 minutes. So go down. Huh? There? Here. Okay, I think there's some issue with this, sir.
It's 3 square.
So 3 square. So sorry. So this is actually 27. Thank you for reminding me, because this video would have gone like this only. So thank you for reminding me. This is 3 cube is 27. 27 by 12 is something. And now what's the answer? Okay, something like this. And here this is 1 cube is, and this is same. So basically what we are saying is IY is less than this. Okay, it's 3 cube, which is 27. Anyway, IY is less than XXX. So Euler asked us to say, Euler will ask us to take I value which is lower. Okay, so now I'm at this point where I write this as both ends hinged. I want to calculate this, both ends hinged, and the other one is one end, what? Is it hinged? Is it hinged? Will you call it as hinged? One end fixed. One end fixed, other free. Other free. And can you imagine any other cases, guys? One is both ends hinged. Other is one end fixed. One end fixed. So that means this, it is fixed here like this. The other end, so can you imagine? So can you imagine the other cases? So other case like one end fixed, one end fixed here, and the other end you can hinge it like this. You can hinge it like this. Guys, now can you imagine now what happens when you do this? In this case it will bend like this. In this case it will bend. But in this case, when I fixed on one side, when I fix on one side and when I apply loads, so can you understand how it bends? Like this. Okay. So this case, you can see that the bending would happen something like this. Okay. The length here is LE is actually equal to L by root 2. It is not L by 2, it is L by root 2. LE is L by root 2. Can you imagine any other case? any other case. So this is both ends hinged, one end fixed and other end is free. And what is this case basically?
One end fixed.
One end fixed, other hinged, other hinged. So can you guess one more type?
Both ends fixed.
Both ends fixed. So both ends fixed. So when you have something like this, when I wrote something like this, and you ensure that you have a slider which holds this between this and where you can apply load. Is it seen here up to you? Okay. Now can you imagine how it would actually bend? Can you imagine how it would bend now? Now this is like this. For this case, it was end like this, it bent like this, it bent like this. In this case, you are actually trying to hold on both the sides and it's going to bend like this. Okay, so it will start bending like this and you will see that this effective length where it is actually bent is actually equal to, this LE is actually equal to the actual length divided by 2. Okay, so just as per the Euler, you just need to know the Young's modulus of the material, I minimum, which is actually BDQ by 12 of the section. Now from the end, suppose if this is the beam, then from the end, how the beam looks. For that you need to find out I minimum. So I minimum is here, I maximum is here, and therefore you need to find this and then substitute this LE value. LE is given, and for that you now should know what is the end condition. For that end condition you should substitute. Okay, if you actually see this, if you write this formulas here, substitute these values here. Substitute the values here. For this case, it is pi square EI by L square. For this case, it becomes pi square EI by how much?
L by 2L.
4L square, because L 2L whole square, that becomes 4L square. So for this case, it becomes pi square
L by 2.
E divided by, so L square by 2, which becomes like this. So for this case, so it becomes pi square by E divided by L by 2 square. So L square divided by 2 square, 2 comes above 4 square. Now you can say that here, if you compare the load capacities of these beams, so PCR, the crushing loads capacities of these beams, for the same beam, you can say that when compared to this beam, you can actually figure out that this pi square EI by L square is common for all this. It is common for all this. Okay, so you can say that this beam is 4 times weaker. So that means if this can take 100 kilonewton, this only can take 25 kilonewton because it is 1 by 4. Okay, so sorry, not beam. This column is 4 times weaker than this. What about this column?
2 times stronger.
It is 2 times stronger than this column. What about this column?
4 times.
It is 4 times stronger than this column. When you hold like this, on both the sides, it becomes 4 times stronger. And when you hold like this, one end fixed and the other end hinged, it becomes 2 times stronger. When you don't hold on both sides, when you have one end fixed, other end free, it becomes weak by almost 2 times. So you can compare it with the standard size, standard which is actually both ends hinged, you can compare with this. So this is how the Euler's formula could be used. Only in the numerical, they will ask you to find the Euler's load for the column with the following dimensions. They will give you the cross section B and D and the length of the column. They will give you Young's modulus value. You just need to find PCR. They will give you what type of condition is it, out of the 4 conditions, then you can solve the problem. This is how you use the Euler's equation.